Hello, everyone, and welcome to our MEC 569 presentation about our autonomous drone project. My name is Daniel, and I was joined by my teammates Peter and Usman. Okay, so the main objective of this project was to program a drone to take off from one landing pad, navigate an arena filled with obstacles while avoiding and detecting them, and land on another landing pad. Afterwards, the drone would take off from the original landing pad, from landing pad B and return to its original landing pad A. Okay, so we'll start with the drone taking off and stabilizing at a defined height for the algorithm structure. After this point, the multi-ranger deck is used to avoid obstacles within set thresholds, since this controls obstacle detection. And then for the search and scanning behavior, we use the Z rangefinder, which controls the measures altitude. Sorry. Now, along with avoiding obstacles, we also set boundaries in the drone in the X and Y direction so that the drone can search a more precise area. Lastly, it uses the range and flow feedback to land accurately. Also, the picture on the right is the actual arena that was used in class. Okay, so there are four main testing phases. The first is the hover stability test, where we make sure that the drone itself is stable while in the air. Secondly, we tested its ability to detect and avoid obstacles. Then, we made sure that it was able to land properly. After testing all of these aspects separately, we performed a final run combining everything. The GIF on the right shows a mock obstacle course that we made in preparation for the actual flight.
Now, going more in details of the code, we utilize Crazyflie's high-level and low-level commander functions to control our drone. Mainly, we're using the low-level option as it gives us control over the pitch, roll, yaw, and altitude of our drone, allowing us to precisely move it throughout space. While the high-level option is used at the beginning, as it's a good way to start the takeoff of the drone and for smooth and controlled takeoff, basically. With that being said, we start the takeoff function using this command, and in order to stabilize the drone, we first get it off the pad, stop all momentum, and then we set it to a target height of about 1.5 feet, which is a consistent altitude we are going to be using for our obstacle avoidance loop. Now, getting into the obstacle avoidance function, uh, the function continuously reads data in all directions from the multi-ranger deck and uses a series of if statements to account for obstacles. For example, if the front sensor is triggered, the procedure is to stop the drone, determine which direction, left or right, has more space, and then turn 180, 80 degrees per second, about 90 degrees in that respective direction. If, for example, the left or right obstacle is detected, we add a roll velocity in the opposite direction to strafe past it to avoid it. Now, finally, in order to minimize the search area, we use a series of boundaries or simply checkpoints to update and limit the search area for the drone. The logic works by monitoring the current X and Y position of the drone and then updating the initial position every time it exceeds a certain distance, such as 2 meters, 3 meters, 4 meters, etc. If the drone tries to move past the boundary, the drone will move back at a certain velocity and then turn either 110 degrees or 180 degrees back in the opposite direction in order to avoid it. Now, the obstacle avoidance loop will break if the target height is exceeded by a certain threshold and is over the pad for a certain duration of time, about 0.2 seconds. Then, the loop breaks and we go into the land and relaunch function where we gradually decrease the altitude until touchdown. And then if we want to relaunch the drone, we send a series of 200 commands over 2 seconds to prevent timeout of the drone in order to take off again. And then simply we just turn 180 degrees and use the same takeoff and avoidance sequence as before. And these functions, along with a few reset and setting functions, is what allows us to successfully land the drone from A to B and then B to A.
These are results and performances. These are our top three trials. The first wasn't successful as it hit a wall and crashed. The second wasn't successful because while it reached A, it missed a landing pad and landed on the ground. The final test was successful as it went from A to B and B to A without any issues or collisions. A common issue throughout the test was low battery as it caused the sensors to perform incorrectly. This is our flight demonstration at 1.25 speed. So the drone starts off, it goes forward, sees the ground, stabilizes to 1.5, sees the object in front and makes a left. Right now it's heading towards our Y boundary and it goes back. It also hits our 1 meter boundary and has to go back again. Now it goes through the obstacles, but it is strafing left and right whenever it sees something. And it's going to landing pad B in line. Once it reaches B, it takes about a second to land. Once it lands, it starts up immediately and makes a 180. It's going back to the original path it took this time, and it's heading towards the obstacle on the left. It detects it and makes a left into another object and makes a right. Over here, it's going towards the Y boundary again, and it detects it, goes back, makes a left into the 3 obstacles. It's going towards the obstacle, stops, and makes a right. Now it's heading towards the end of the arena boundary or the end boundary. Once it reaches there, it stops, goes back, makes a left, and then now it hits the last boundary that we have after the obstacles. Hits that again, goes around. This time it's still not at a great angle to hit the landing pad, so it hits the end boundary, makes a left, goes towards the wall, makes a left again, this time going to the last boundary, which goes back and then makes a left, and hitting the end boundary, where it goes back and makes a left again to the last boundary, goes back and makes a left, this time in line with landing pad A. It detects it and is able to land, and these are our teammates in the video. So reflections and future improvements. Lessons learned: slow is smooth and smooth is fast. Since the obstacle range is limited, it's best to tune it to a safe distance. Landing precision improved after code touch-ups, and battery level influences the drone performance. For future work, we can gradually increase speed for the most optimal time. We can add adaptive obstacle detection, which adjusts based on the flight speed and sensor noise. And we can predict obstacle positions instead of reacting only when detected. And that was our presentation. Thank you.